I want to start by sharing why am I here today. And I'm here today because the last couple of years have been very colorful to me. And I mean literally colorful because I've spent a lot of time looking at graphs like this. This one, for example, is the garbage collection cumulative time in our services, or this one is the distribution of garbage collection time. And we'll discuss garbage collection soon. But for now, take a look at this graph. And you can see that there are collections that are more than 2 seconds. Now, for a service that serves hundreds or thousands of user requests, you can imagine the impact of a garbage collection pause that takes 2 seconds on the user's experience, because garbage collection in Python is a stop-the-world operation. It means the entire process stops to handle garbage collection. Now, how many of you have experienced performance issues with their Python application? In a show of hands, please. Okay, lots of you. And we did too. And I'm here today to share some of the experience we've collected in the last couple of years, especially that regarding to Python memories management. And I hope you can use this information to improve your own Python applications. A little bit about myself. My name is Michael, or Miki. I'm a software engineer at Meta, also known as Facebook. I've been there for just almost 3 years. Most of the time, I've been in part of the Novi product, which is now Meta Financial, Meta FinTech. Novi, if you didn't know, it's the wallet for the cryptocurrency, the stable coin that Meta was part of. And my team was responsible on the storage system for the Novi app. We've built an ORM, mostly in Python. And we've experienced a lot of memory and performance issues. Right now, I'm part of the authentication services team, working on the Meta's family of apps authentication. So this includes Facebook, Instagram, and WhatsApp. And I'm here today to share with you these topics. Now, our talk will be split into 2 parts. In the first, we'll cover the bases. So what is the Python object, how variables or names work in Python, and the methods Python uses to manage memory. And in a second talk, we'll discuss some memory optimization techniques you can use to improve your performance, and we'll even see some case studies from Instagram. And final notes before we start. This talk will be focused on the CPython implementation for Python 3. This is the standard implementation for Python, so this is the one you're likely using. It will include some C code, but you don't really need to understand C to understand the talk. And this talk will take the full 25 minutes, so there will be no time for Q&A here on stage, but you can catch me later and I'll be happy to answer all of your questions. So let's start. And we'll start with a very simple program written in 2 programming languages. One is written in C and the other in Python. And after each line, I'm printing the memory address of the relevant variable. And you'll see that there is an interesting difference between C and Python. And probably if you would have to guess, C is the expected behavior you would think of a normal programming language. So let's see what happens. And in C, the X and Y's are indeed called variables. In Python, it's a semantic thing, but they are actually not variables, they are names. And names reference objects. So let's see what happens here. We'll go line by line. So in the first line, X equals 1000, what happens is that we create a Python object. In Python, everything is an object, including integers. So this object is created on a heap, and X is a name, and it references that Python object. And the interesting thing happens on the second line. When we execute Y equals X, we create a name, a new name, not a new variable or an object, and that name references the same Python object. And finally, when we execute X equals 1001, we create a new Python object because integers are immutable in Python, and this is why the memory address changes. Now in Python, everything is an object. This includes integers. And under the hood, Python object is a very, very simple C struct. You can see the code in front of you and you can ignore the black magic syntax of C and see that it only has 2 interesting members. A reference count, which we talk about in a minute, and some type information, which includes some metadata about the type, like the name and things that will have the garbage collection. And by itself, this Python object doesn't do anything special. If we want to use it, we have to extend it. So for example, the integer values you saw before, they are extension to that Python object with a size and a value member, and that becomes the integer. And finally, it has a reference counter. And this brings us to the first method Python uses to manage memory. So what is reference counting? It's a technique for managing memory, and the idea is that we can get an immediate deallocation of objects as soon as we no longer need them. Now, it's important to note that when I say deallocation here in the next slides, I mean that the memory that was used for that Python object is returned back to Python to decide what it wants to do with it. It might use it for a new Python object, or it might free it back to the operating system. Now, it's not only Python uses reference counting, it's a common technique, and C++ and Rust also uses that as well. So let's take a look at the same example from before with an added statement in the end and see how reference counting behaves. So in the first line, as you would expect, the reference counter is 1. And when we add the reference from y, it increases to 2. When we modify the value of x, it decreases back to 1, and the new Python object is created with a reference counter of 1. And finally, when we execute delete y, in this context, delete y means removing the name y. And with the name y, the reference is also removed, and the reference counter is decreased to 0. And we can safely delete the object completely. Now, reference counting has some advantages, but some very interesting disadvantages as well. So the main advantage, and this is the one we talked about, is the immediate deallocation. The fact that we can remove the object immediately. It's also pretty simple to implement and much more simple than other techniques for garbage collection. Now, the disadvantages, the first one is an overhead. So for example, every line you execute, almost every line you modify a reference counter implicitly. So this means an increment or a decrement operation for almost every line you execute. It also has a space overhead because now every Python object have an additional bytes used to manage the reference counter. It is also the reason why we have the GIL, the global interpreter lock, because we don't want two competing threads modifying the same reference counter, causing memory issues. And finally, it does not handle reference cycles. So to understand reference cycles, let's take a look at the following example. There's another very simple code where we have a node class, which all it does is reference another node class. Let's go line by line. So in the first lines, we create two node class and we close the loop. So now they point to each other. Each one has a reference counter of 2. The name and the other node points to it. And afterwards, we delete the names. We delete A and we delete B. And we are left with 2 Python objects, each with a reference counter of 1. They're floating in the memory space and they will be never removed by reference counting alone. So we must have a complementary method to handle those type of objects. And this brings us to the second technique Python uses to manage its memory, and it's its tracing algorithm. And usually when people say garbage collection, they actually mean the tracing algorithms. And it's a very common technique, probably the most common technique for automatic garbage collection. Java uses that as well. And the idea is to detect those unreachable objects. Now, there are different algorithms exist. I'll briefly go over the Python one at a very high level. So in front of us, there's 2 names, X and Y are names, and they reference objects, and those objects reference each other. Now, you'll see that inside each object, I denoted the reference counter of that object. Now, an important note, and please remember that for the end of the slide, because it will be relevant for the end of the talk, this reference counter is not exactly the same reference counter that we saw before. It's a copy of the reference counter used by the garbage collection algorithm to handle the algorithm itself. And how it works is by iterating over all objects. For each object, it reduces the reference counter by 1 of all objects it references. So this one is reduced to 0. And then it does the same for all other objects, and we reach a final state which looks like this. Now, the question is, can we safely remove all objects that have a reference counter of 0? And the answer is no, because there's an object in the middle with a reference counter of 0, which is still reachable from X. So we have to do something else, something additional. So very high level, what Python does is it has a list of potentially unreachable objects. And all those zeros are potentially unreachable. And it does another iteration where it goes over all of the objects, and those that have a reference counter greater than 0, it increases the reference counter of all objects it references by 1. And when it completes this iteration, all of the objects that are left with a reference counter of 0 that are left in their unreachable, potentially unreachable list can be safely removed. Now, an ancient Chinese proverb once said that most objects die young. And Oracle actually proved that somewhat in the 80s. They did a study where they measured for each byte that was allocated, how much time did it survive for? And they saw that most bytes did not survive for a long time. Most bytes were allocated and deallocated pretty fast. And you can imagine how it makes sense. So think about for loops, where you execute a small function or a small piece of code over and over again. Those objects will live for a very short period of time, only one of the iterations of the for loop. And Python and also other programming languages use this for the advantage of their implementation for the algorithm by doing something that is called generational tracing. And the idea is to collect more frequently from younger objects because there's a high likelihood that they will be really collected. So what Python does is it splits all of the objects into 3 generations. And remember, again, remember the 3 generations because that as well will be relevant for the Instagram example. Now, the Gen 0 is the youngest one, where all newly created objects start there. And for each collection in a given generation, so for example, Gen 0 is collected, all of the objects that survive the collection are promoted to the next generation. And the idea is to collect more from younger generations. And when we collect, for example, from generation 1, Python also collects from all the previous generations, and the same thing applies. Those objects that survive the collection advance to the next generation. And you can imagine how the last generation collects over the time objects that some of them live from the start of the program. And collections in the old generation might become very, very expensive. Those 2 seconds that you saw in the start of this talk were from that last generation. Now, another small optimization Python does is it only tracks container objects. It means that non-container objects like integers or strings are ignored during the collection because they cannot be part from a reference cycle by themselves. Okay, so we talked about the basics and how memory management works in Python. Let's see how you can leverage that information and see other techniques you can use to improve the memory of your application. And the first might be the most trivial one is slots. Now take a look at this very simple class in front of you. It has only 2 members, x and y. And I initialize it with a small integer and the value hello, which should be small in size. But when I print at the last line, the size of this class, the size of the instance, it's over 300 bytes. It's crazy for such a small object. And the main culprit of this size is the dictionary. So in Python, almost all objects have a dictionary. All objects you usually create, all instances of classes you create has this dictionary. And this dictionary is used for the attribute access for this class. It's from the members, from the attribute names to their actual value. Now with a very simple change, 1-line change, where we add slots at the beginning, slot equals x and y, we change the class, but we almost don't change the usage. And you can see at the last line that when I print the size of this class now, it's 130 bytes. This is a 60% reduction of the size class. Now, what it does basically, slots, it replaces the dictionary with an array. Now, the access to the attributes in the class are a random access pattern and not a dictionary lookup. So it also improves the attribute access performance. And the idea is use slots for those classes that you have a lot of instances for. those utility classes you also spread all over your code and you create a lot of instances for, and it can significantly improve the memory footprint of your application. There's almost no disadvantages. One disadvantage, though, that it's important to note is that you can't add, in this implementation, you cannot add a new attributes. But if you're using typed Python, you probably don't want to do that anyway. Another optimization you can do is C extensions. Now, CPython is implemented in C. So it should be relatively simple to extend Python with C. Now, it's probably a blasphemy for me saying that in a Python conference, but C and C++ are much faster than Python. And in Novi, what we did is we used Cython, which is a kind of programming language that helps you create C extensions for Python to change the low levels of our ORM, and we gain a 15 times improvement of performance, both on CPU and memory. And you don't have to write a single C function to improve your code with C. NumPy and Pandas, for example, are implemented in C. So you can use those. Don't write your own special code that is already implemented in Pandas or NumPy. Use them and you'll gain a much bigger performance improvement. And finally, I want to finish with some lessons from Instagram that relate to what we saw before. Now, if you didn't know, Instagram is actually implemented in Python. The backend is in Python. It uses Django and Uwisgi. Now, in Uwisgi, there's a concept that there's a main process that forks child processes that handles requests. Now, there's another mechanism called copy and write, which Linux uses, which helps to reduce the memory footprint of child processes. So what happens with copy and write is that when we fork a process, we don't need to fork the entire pages of memory for that process until we modify them. We can use the same memory blocks and addresses unless they were written to. Now, when the engineers at Instagram, when they profiled their backend, they saw that they have a lot of page faults. And they went and investigated those page faults, and they saw a very interesting thing. They saw that the collect method in the garbage collection module was responsible for most of the page faults. And then they thought about it. What can happen here? What is the case? Now, if you remember from the slide where I showed you the tracing algorithm, there's a reference counter value inside each Python object, which is being modified by the garbage collection run. And they saw that the moment garbage collection kicked in the child process, the page faults happened. And because the garbage collection algorithm runs over all objects, modifies all of those reference counters, and basically writes to the entire memory space of the process. So garbage collection disables the benefit of copy and write. And what they did was very simple yet very aggressive. They went ahead and just disabled garbage collection completely. I mean the tracing algorithm, of course, not the reference counting. And they pushed it to production. And what they saw is that it increased their capacity. The entire fleet of Instagram capacity increased by 10% from disabling garbage collection. Of course, there's a big disadvantage because we don't collect those reference cycles. So what they did is they monitored the processes, and when they reached some threshold in memory footprint, they just killed it and restarted it and had a new process. Now, after some time, more features were added to the backend of Python. And they saw that they couldn't keep up with the memory growth because they had to kill their services over and over again. And they basically didn't handle enough user requests to make it efficient. And then they went back to the drawing boards and their conference rooms, and they thought, what can they do? And they understood they needed a better solution. And their approach of disabling garbage collection completely was not refined. It wasn't exactly what they wanted. They wanted to disable garbage collection for only the relevant part of the memory address blocks of the main process. And what they did is very interesting. They went ahead and contributed to the Python open source implementation, a method that you can use by yourself It's inside the GC module. It's called the freeze method. And if you remember, as I showed you the 3 generations, what freeze does is add a 4th generation. And that generation is called the permanent generation. Now, when freeze is called, all of the objects in the 3 generations are moved to the permanent generation. And when garbage collection, the tracing algorithm kicks in, it doesn't look at all at the objects in the permanent generation. And then all they had to do is call freeze just before they fork the process. All of the objects that leave from before remained in the permanent generation. New objects created started at the young generation, generation 0, and the benefit of copy on write remained. And the memory growth improved as well because they still have the tracing algorithm for all the new objects. And you can see this graph. This is before the change. The blue line is before the change of the second idea of the freeze method. It's the memory growth, and the red one is after the change. And in Novi, if you remember the example from the second slide, I think, we used the same API. We had a server set up where the server did a lot of heavy work before accepting requests and created a lot of objects, caches, and many, many things that we knew that they will live for the entire lifetime of the process. So the only simple thing that we did is just call GC freeze before we start to accept new requests. And we gained an improvement, you can see here, of the collection time distribution, and we had less of those very, very heavy collections. I want to wrap up with a summary of what we discussed today. So we learned that Python actually has names and not variables, and those names reference Python objects. And we saw what are those Python objects. We also learned the 2 techniques Python uses to manage its memory, its reference counting, and the tracing algorithm, the generational tracing algorithm. And finally, we saw some optimizations you can do tomorrow, very simple one, slots and C extensions, and we even saw some case studies from Instagram. I really hope you can use what I showed you today to go back to your offices tomorrow, or home offices, and implement some of these changes, because some of them are very, very simple and can benefit you a lot in your Python applications. Thank you very much.